Okay, what questions do y'all have over optimization stuff before we move on? Yeah. As soon as it finishes loading. Okay. So we've got a line segment of length square root of 23 meters. That's pretty long. And we're going to put it at an angle. It could be long like that or sort of tall. You could get a cone like that. Or if it's flat, same length, right? This is still 23 meters. You could get kind of a squatty cone like that. Okay, so the orientation of how we put this in is going to give us different cones. But we do want the restriction to that if I draw the radius in there and I draw the height up, that's going to give me a triangle, a right triangle in the middle of my cone. And so I want to restrict things to r squared plus h squared equals 23. Sorry? Okay. So this right triangle gives us this, the restriction or the constraint function. Okay. The objective function is we want to find the cone of the greatest volume. So the volume of a cone is equal to 1/3 pi r squared h. So the easiest thing that I see to replace in here would be the h squared, because I can solve for r squared right here, and then I won't have to actually have a square root anywhere in my function. So I'm going to solve for r squared. And we know that r squared is equal to 23 minus h squared. So this is our objective. This is our substitution. So I get the volume as a function of h is 1/3 23 minus h squared times h, which is, sorry? Is it 1/3? What? Yes, yes. Put a pi there. Thank you. Okay, so we got 23 pi over 3 h minus pi over 3 h cubed. So v prime It's going to be 23 pi over 3 minus pi h squared. So we set that to 0. Pi's cancel. You get h is the square root of 23 over 3, which we can now solve for r squared. That's going to be the square root of 46 over 3, I believe, because I want 2/3 of it there. Because h squared equals 23 over 3, r squared plus h squared equals 23. So if 1/3 of it's there, 2/3 of it has to be there. That's 2/3. I'm going to square root. I don't want the squared there anymore. So there we go. Height, square root of 23 over 3. Radius, thing. And then the volume, we can just multiply these guys together. So volume is 1/3 pi. R squared is 46 over 3, and h is square root 23 over 3. So 46 square roots of 23 pi over 9 square roots of 3. Where do we have questions on that? Here. What numbers do I have in the denominator? I've got a 3, a 3, and a square root of 3. So that's a 9 square roots of 3. And in the numerator, I have a 46, a pi, and a square root of 23. Other questions? Yeah. 19. We've got a cost function in terms of cost per unit, or inputs are units and outputs are total costs. We want to find a production level that minimizes the average cost. So we have to first come up with an average cost function, and then we want to minimize it. So if C of X is the cost of producing X units, the average cost, what do you do to find an average? Divide by the number. So that's going to be C of X over X is the average cost function. We want to optimize this. It's already just in one variable, so we can just take a derivative of that. But a of x, let's write it out. That's going to be 6x squared because I'm dividing by x minus 36x plus 2,000, 20,000. Because I divided by x, I reduce all those exponents by 1. So a prime of x is 12x minus 36. And then this is 0 when x equals 3, because that's an easy one to solve. We'll put 3 in there. At this level, the average cost of making x items is, now we just put 3 in the average cost function. So I get 6 times 9 is 54 minus 36 times 3, which is 108. So I've got 54 minus 108, which is just minus 54, plus 20,000. That's going to be 19,946. Questions? Tricky parts there, recognizing it's the average cost function you want to memorize, maybe. Other questions you want to see? 13? Okay. We've got x cubed plus ax squared plus bx, and we want for a, we want a max at x equals minus 5. We want a min at x equals 7. Okay. So to do that, I need my first derivative to have roots at -5 and at +7. So I'm going to take the first derivative. I'm going to get 3x squared plus 2ax plus b. And we want this to equal 0 at -5 and 7. So I can put 5 in, -5 in, and get an expression. I can put 7 in and get an expression. So I'm going to put 3 times 25 plus 2a times -5 plus b equals 0. I'll put 7 in. 3 times 49 plus 2a times 7 plus b equals 0. And now I have a system of 2 equations and 2 unknowns. So we'll move things over, sort of simplify stuff. Minus 10a plus b equals minus 75. And I've got 14a plus b equals 147. And let's subtract the top one from the bottom one. So if I do that, I have 24a. The b's will cancel, equals 222. Yeah. So a is going to be 111 over 12, which factors a little bit more. That's 37 over 4. So if that's 37 over 4, B, which one's the simplest to solve for here? This one maybe? (14 times 37 over 4 plus B equals 147. So B equals, well, maybe that's not the easier one to work with. I like working with multiples of 10 better, so let's do multiples of 10. I've got negative 10 times that plus B equals minus 75. 370 over 4 equals 75 fourths, or sorry, 75 in fourths is 300, so that's going to be 70 over 4, or 35 over 2. So I got 37 over 4 for A. And 35 over 2 for B. Where did I screw up my arithmetic? Oh, this is minus, isn't it? Yep, that's a minus sign. So I need a minus sign there. That changes all this stuff. Okay, minus 147 plus 75 is going to be a minus 72. I like that better because that makes that minus 3. Minus 3 is a much nicer answer than we had before. Okay. And then minus 10 times minus 3 plus B equals minus 75. So that's 30 plus B equals minus 75. B equals minus 105. A was 3, minus 3. B, minus 105. Check that. Okay. What do I do here? Part B. Yep. So I still have 3x squared plus 2ax plus b equals 0 at x equals 10, so I can still get that one. So that's 300 plus 20a plus b equals 0. And for the second derivative, the point of inflection, I have that 6x plus 2a equals 0 at x equals 1. So 6 plus 2a equals 0. That tells me a equals minus 3, right? And if a equals minus 3, I get that 300 plus 20 times minus 3 plus b equals 0. So 300 minus 60 plus b equals 0. So b equals minus 240. So a is still minus 3. B is minus 240 this time. What do we have questions on that? You're just using the derivatives to sort of figure out some expressions that you can solve for your variables that are missing. Anything else you guys want to talk about? Okay, just a quick thing with Newton's method, and then we're going to do some examples. So Newton's method is a way to approximate roots of a polynomial, and I'm going to draw a picture first. So it doesn't actually have to be a polynomial even. It's just roots of any function. So I look at this picture. And maybe this is at 1, 2, 3, 4, 5, 6, 7. And let's say I'm trying to find this root between 3 and 4. Well, what I'm going to do, let's put those tick marks further apart. They're just going to make the picture nicer. Okay. So I'm trying to find the root that's about halfway between 1 and 2. So what I'm going to do is I'm going to guess at which one I'm trying to move to. And let's say I'm trying to move to here. So I'm going to make a guess of 2 because in my head, maybe I think 2 is the closer one. So I'm going to come up to the graph and see how close was I at 2. So I'm going to plug 2 in. We'll find out what that is. And then it's not equal to 0. So I know that that's not the specific root. But I want to get closer to the actual root. So what I do is I draw the tangent line in here. And I follow the tangent line down until I get to this point, this new point on the x-axis. So we're going to say that our first guess, our 0th guess, our initial guess, x0 is at 2. We're going to go up to the function. We're going to go down along the tangent line. We're going to get our next guess at x1. And we do that again. We come up, we follow the tangent line down, we get to another guess. And if this is polynomial, this thing works really pretty well usually. And these go up to the function, slide down the tangent line. That's my next guess. That's really sort of simple to codify. The next guess is equal to the first guess minus how far I would have to travel in the x direction. And how far you have to travel in the x direction depends on both how high you were up and what the slope of the tangent line was at that point. So that's going to be f of x, this is n divided by f prime at xn. That's the slope of the tangent line. That's how high up you were. So how high up you are divided by the slope is how far in the x direction you travel, right? Sort of, this is delta y from 0. This is delta y over delta x. So you take delta y divided by delta y over delta x, you end up with delta x. So you take xn minus delta x, and you get back to your next x guess. That's what this is. And so Newton's method is just apply this thing until you get to as good of an approximation as you want. Sort of zooms in. There are some problems. It works a lot of times, but there are some graphs where this doesn't work. Say you have a graph that kind of looks like this, right? And if I start with like a guess here, this thing's going to shoot me all the way off over here. It sort of is a bad guess. So maybe I think I can find someplace in here a little bit closer. And what that does is it shoots me down to here. And then this thing shoots me back to like where I was. And then I just kind of get in this trapezoid thing, not trapezoid, parallelogram thing where I just sort of circle around here indefinitely. And that doesn't work very well. Okay, so this works a lot of times, but sometimes it doesn't. And that's basically Newton's method, is just repeat using this thing to get approximations for roots of polynomials. Okay, let's do some examples from the next section. So we'll just do this one. So we want to start with x0 and end up with x2, so I got to use Newton's method twice. And it tells us x0 is 0. So I have the function f of x equals x cubed plus 4x plus 2. So f prime of x equals 3x squared plus 4. And so remember, xn plus 1, the next guess is the current guess minus f of x, the current guess over the slope at the current guess. So it's going to be xn minus x cubed plus 4x plus 2 divided by 3x squared plus 4. These are all n's. So x1 will be x0 minus x0 cubed plus 4 x0 plus 2 divided by 3 x0 squared plus 4. We're told that x0 is 0. So x1 equals 0 minus, well, that's 0, this is 2 over, that's 0, 4. So that's minus 1/2. We're going to do the same thing with x2. That's going to be minus 1/2 minus minus 1/2 cubed plus minus 1/2 times 4 plus 2 over 3 minus 1/2 squared plus 4. Now I have to do some arithmetic. This is minus 1/2 minus minus 1/8 minus 2 plus 2 over 3/4 plus 4. So it's minus 1/2 minus, those guys cancel, minus 1/8 over 16/19 fourths, which is minus 1/2 plus, I've got a 4 on top, I've got a 8 and a 19 on the bottom. So that's minus 1/2 plus 1/38, which is minus 19/38 plus 1/38 is minus 18 over 38, or minus 9 over 19. We're going to go minus 9 over 19. And that was Newton's method with 2 iterations. And that's going to be pretty close. Let's plug it in and see actually how close we are. Get a graph here. So the blue line is our approximation. The red is the actual function. So we're really pretty close. I have to zoom in quite a ways before I see that that's not actually the root, right? We're not actually the root there. We're just a little bit too much. Okay. And so what Newton's method is going to do the next time is it's going to take this point, it's going to slide down along the tangent line of the red thing, and it's going to end up like right in there. Okay. So it's going to get even closer the next iteration here. Spot on. You can set up functions where it will, but really it's just an approximation method. You can set up tolerances and you can figure out how long it'll take you to get within that tolerance based on the original function. But really it's an iteration method to get to a certain point. It doesn't actually solve. Yeah. Okay, so this gives you 2 iterations. I'm going to take x0 as my first test point equals -3, and then I'm going to use 3 as the other one, and those will bring you in to 2 different roots. Let's look at maybe something later in the assignment. So here it doesn't even tell you what you want to use as test points, so you can kind of just throw one in and see where it takes you, and throw another one in and see where it takes you. Or I might graph this. Get rid of that guy now. And there's two roots there. One is around 2/5. So maybe I put in a half, start with a half, that's going to bring you here. You're going to follow the slope down, it's going to get you closer. You can come back up to here, follow the slope down, it'll get you closer again. And then you could use 2 if you wanted to. And if you use 2, you start here, you follow the slope down, you end up way up here. 2 might not be a good one because it's going to push you here, and that's going to push you to a really big value up here, right? And then you have to follow that slope down. It might work okay. I'd maybe try 2 1/4 and start up here, follow the slope down. It looks like that one will get you faster. 2 1/2 maybe. 3, yeah, not 2 1/4. 3's right there. So maybe start at 2 1/2, which starts you there and brings you down instead of starting at 2. 2 doesn't have a very big first derivative. The slope there, it's kind of wide, which means it's going to kick you out farther because the slope's in the denominator of this approximation. So when that denominator is small, your iteration, it changes things a lot. So if you have a really big denominator, it's not going to change things very much. So there's a couple roots here, right? This looks like x naught. This looks like x squared times 3. Sorry, factor out the 3 first. And I've got x squared times x squared minus 1. So it has 3 roots. It has a root at -1, a root at 0, and a root at 1. Right? So if I graph this, I should have roots at 0, 1, and -1. Okay. So if we look at this, using Newton's method with different starting points is going to take us to different roots. Right? If I am here at the maximum, I just have a horizontal line. So picking a maximum or a minimum to have as your starting point isn't very good because you have a derivative of 0, and Newton's method says divide by that derivative. So division by 0 is bad. So you don't want to pick a max or a min. If I start to the left of that, it's going to follow the tangent line down and looks like it's going to get me closer and closer to -1. So if I start left of that max, I'm going to end up at approximating -1. If I'm to the right here, what that's going to do, depending on how far to the right I am, it's going to shoot me somewhere over here, right? If I'm just very barely to the right of that, it might shoot me all the way over to here, right? So at some point in here, it's going to shoot me to probably like right in here. I'm going to be approximating 0. Right? If I'm shooting past whatever this is, square root of 2, if I'm here and the slope shoots me past the square root of 2, I'm going to start approximating +1. So there's some points in here that give me positive 1. Then there's points that give me 0 again, and these guys all give me 0 until I've got some points in here that give me -1 because I've shot past. And then after I'm past this, they're going to approximate 1 again. Does that all make sense? Okay, so that's kind of what this question is asking, right? If x0 is -2, so if I'm over here at -2, clear up there at -2, like all the way up here at like 30-ish, right? Where am I gonna, my slope is really steep. I'm gonna be approximating -1. X sub I is gonna go to -1. As I gets large. Okay. In here, for x is 1/4, so if I'm in here, right, I'm between 1/4 and -1/2. So I'm somewhere in there. Where am I going to go? I'm going to end up at 0. So I'm not going to start alternating between those guys. I'm going to end up at 0. Square root of 2 over 2, that's where this peak is. If I go on any of these guys between square root of 2 over 2 and infinity, where am I going to end up? I'm to the right of this. If I'm at the right of this, I'm going to start focusing in on 1. Okay. This is the one, I believe, just how I had told you this thing all worked. How'd that work? Okay. How this all worked was, there was some point in here where it shoots me over exactly to that point again, right? If I shot far enough, I would end up all the way over here, and then I'd start converging to 1. If I wasn't far enough, I'd shoot myself over into here and it converge to 0. But at some point, what this is going to do, it's going to bounce me over to here, which is going to bounce me back to exactly where I was, which is going to bounce me back to exactly where I was, and I'll just have this sort of alternating thing in here. And we could solve for that. You would want to say, you want to use the iterated method 2 times. If you do Newton's method twice, I end up exactly where I started. So you can put in a variable and get an expression that you can solve for that variable that makes it do that iteration thing. And apparently it's probably going to be square root of 21 over 7, or the negative square root of 21 over 7. And so for these, I'm going to guess that that's the point that bounces me back and forth between itself. Does that make sense? Okay, we'll talk some more about Newton's method stuff tomorrow if you guys have questions. There's not a lot of homework on it, and there's not a lot in the section. just kind of getting used to using the iterated method stuff. So come with questions tomorrow. We might move on to 4.8 if there's not a lot of questions. Yeah. It'll be next week because 4.6 is due today, 4.7 is due Wednesday, 4.8 is due Friday. I think there's a 4.9 which would be due Monday, and so the test would be Wednesday. Is there just 4.8? Then the test is next week. It's either Monday or Wednesday.